everyone. Today I'm going to go over the PBE simulation framework we recently developed. So I will present a few different videos covering different aspects. So in this video, I will go over mostly the practical implementation of PBE simulation, which is something embedded mainly in this demo script that you have in the folder provided to you under the name PBE workflow for publication. You can access this the content of this folder in our most recent publication, which is on the uncertainty sensitivity analysis of CSH precipitation model based on population balance equation. So basically in this folder you have a thermodynamic database, which is basically very similar to PHREEQC databases. In this case, for a cementitious system, I have taken some data 18. I have cut it down to the necessary elements and species that I have in my system to expedite the simulations. Of course, this is more important when you have a huge amount or volume of calculations, as you do in the case of uncertainty sensitivity analysis. For the sake of this demonstration today, it doesn't matter that much. So you can pretty much use another larger database as well. Then you have a few functions. So you have this EQBRM solver. Basically, it provides an interface to PHREEQC so that we don't have to worry about speciation calculations anymore. Everything is implemented within the popular program PHREEQC. In another video, I will go over the content of this file and I will describe how it is implemented. But for the sake of brevity for today, I will stop here about this function. Then we have this function called maximize. So this is something I downloaded from MathWorks Help Exchange. It's a very powerful or maybe helpful, let's say, tool for plotting in MATLAB. So basically, every time you do a plot, you make a plot, you have to maximize it just by pressing this maximize button here. I find it sometimes annoying when I have, for example, like 20 figures, or I have to open and close figures repeatedly. So this one, just by writing maximize, it will maximize the figure window for me. Then I have my PBE, which is the core of this program, which is an engine that does the integration of the ODE set, the ordinary differential equation set. And then we have this subplot function, again another function I downloaded from MathWorks Help Exchange. I'm not going to demonstrate its application today, but if you are working with subplots, then you might want to use this one a lot, because it gives you the possibility to minimize the area and squeeze the subplots together and maximize the plotting area as much as possible. I have used it a lot in my publications. You can check them out and see how it works. There is also a very beautiful introduction within the function itself, so you can also refer to that one. And finally, today we are going over this demo file, which is basically a demo population balance simulation. So first and foremost, the first thing you have to do generally is to add the path where you have your files into the working directory of MATLAB, and we usually do it with this. And this gen path is included here to also include the subfolders, if any. Then we start with defining an experimental system. The idea, let's say, logic behind this part is pretty much similar to what we have in PHREEQC, and that is what they describe as having simulations literally the same as what we do in the laboratory. What that means is, for example, in the laboratory, you can mix different things with known amounts. You can prepare concentrations, you can change the pH, you can set the temperature. We have pretty much the same scenario here, but only with a computer. So we can set, for example, the temperature for our simulations, and then you can introduce what elements you have in your system, and then they introduce the aqueous species. Notably, this list has to be compatible with your database, so the names have to be the same, and the elements or aqueous species that you are introducing into your pod have to be available already with the same names in the database. You can also have gaseous species. This is important, for example, in some cases like calcium carbonate precipitation, or, for example, calcium silicate hydroprecipitation, where, for example, we want to keep a controlled atmosphere. For example, for CSH, we want to keep it under nitrogen with a known partial pressure to avoid simultaneous precipitation of calcium carbonate. Then we have this flag variable. So let me describe what it does. So let's read it. Everywhere we have these comments that describe what each parameter is. Here it says a flag with ones in the first row denoting the elements that have to be equilibrated, forcing a desired partial pressure of the gas with the corresponding index in the second row. So this is basically a matrix with a first row where with the first row where we have the indices of elements whose amount is dictated by a partial pressure. And in the second row, we are introducing the index of the gas corresponding to that element whose partial pressure has to be fixed. For example, here we have only the last element, which is nitrogen gas NTG. Only the last element, the amount is dictated by imposing a partial pressure. And what gas do we use to impose or calculate this equilibrium, or let's say calculation? The first gas. So only we have one gas here, but if we have more gases, we have to also define which gas has to be used for imposing this partial pressure for this particular element. So this is something, again, as I said, following the mindset or logic in PHREEQC. If you are not very comfortable with this idea, I strongly recommend you to find some references and read up a little bit about PHREEQC. It's a bit difficult, but if you want some good starting points, you can just send me an email and I will send you some documentations or some pointers to get started. Then we have, for example, the solid species. In the current version, only one solid can be kinetically precipitated from a solution. This will hopefully change in the future. We will extend it to the case of multiple solids as well as solid solutions. And then we have to also say if we are defining some solids. So you can have two possibilities. You can already, in the database that you're preparing or adapting, you can define your solid, or you can define one solid here. So here in this case, I am defining my solid CSH here, because then I can play with the parameters that describes its formation. Let's say, for example, enthalpy of formation or equilibrium constant, things like that. And this is the index of the solid phase that is not already in the database and you have to define. And for this solid, you need the dissolution reaction. For the precipitation, you need the molar volume of the solid. You need the log K for this dissolution reaction. And finally, if temperature is important for you, you can also put in a delta H or enthalpy of the reaction. There is also a possibility to, in PHREEQC, of course, a possibility to describe using a, let's say, virial type equation. I didn't include it here, but it's very straightforward to also include that possibility into the code. Then we move on to the definition of the experimental system. So first we define mostly the thermodynamic conditions. We only define the temperature of the system. Maybe it's better to even I just copy and paste this temperature down here to put it beside the rest of experimental conditions. I will maybe put it somewhere here. elements initially in the reactor. It's something, okay, it's maybe better here. And concentrations are at room temperature, for example. I just maybe remove this. Okay, this is also important before I delete it. So we have initial volumes and concentrations reported at room temperature. So the experimental data I am using in my simulations, or better to say to compare with my simulations for regression for different purposes, are all at room temperature. That is what this is here. But you can set in any temperature. So the simulations are capable of handling any kind of simulation. At the end of the day, the element concentrations you're putting here are supposed to be the ones you measure at room temperature, and that makes sense. When you are preparing your solutions, you're preparing everything in a, let's say, room temperature. So if you are reporting the concentrations, as we are doing here, in terms of units other than moles per kilogram water, for example, moles per liter, then they are usually at room temperature. So this is something worth mentioning. Then we have the concentration of different elements inside the reactor at time 0. So here we have a semi-batch reaction vessel. It naturally also applies to a batch reaction vessel in the sense that then the inflow concentrations will be 0. Everything will be inside the reactor from time 0. Then the gas is the in PHREEQC, the saturation index for gases is basically the partial pressure of that gas. And this is what we have here. So basically this means that nitrogen gas, the amount of nitrogen gas dissolved, is calculated by imposing a partial pressure of, let's say, 0. A partial pressure, which is 10 to the 0, or let's say 1 atmosphere. My bad. So this is gas SI is log of partial pressure. Then we have the volume of the reactor at the beginning, how much solution you have at the beginning, how much solution you want to add as the added stream, what is the flow rate of that stream that is being added, and if you want to fix the pH, you can also set it to a fixed value. For example, if you are doing titration experiments where you are also fixing, for example, the pH using sodium hydroxide, you should also say the compound I'm using for fixing the pH is sodium hydroxide. If you're using, for example, HCl, you have to put in HCl. And again, the names have to be compatible with what you have in the database. And then here, you have to also say what element is being affected by this fixing the pH. So the amount of this element will be calculated based on fixing the pH to this set value. Then we will move on to kinetic parameters. We have also different kinetic parameters. In this particular case, we have the interfacial tension, relative cohesion energy, growth rate coefficient, kinetic order of growth, and the edge length to thickness ratio for crystallites. In which case, in this case, we are assuming we have cuboid shaped crystallites, and that is what we are putting here. Then we have the stoichiometry of the solid. This is something that we are not passing to PHREEQC, so that is why I am introducing that additionally inside PHREEQC. These are already calculated from this reaction, but for kinetics, I have to also provide this separately. So this is also the sum of the stoichiometry coefficients for a species forming by the solution, except for water. Like this is basically how many ions you are producing upon the solution, or how many, let's say, neutral species, neutral aqueous species and ions are forming as a function, as a result of the solution. Then the time steps at which you want your PV simulation output. So basically, I want a higher resolution at the beginning, so I set it with 60-second resolution at the beginning. Then I would like to also have more data every, let's say, 10 minutes after 4 hours. You can, of course, play with it. Usually 12 hours precipitation in this example was sufficient to reach more or less equilibrium with normal parameters. Then I have to always load a database and the server for interacting with PHREEQC. So basically we are using this so-called PHREEQC COM object. So we have to always load it. And then once we activate this server, we have to always, let's say, activate the server. And once we activate this server, this is an object, I have to load the database and put the name of the database here. Now this PWD is nothing but the current directory address. So if you go back here, this PWD is basically like this. Or you can just simply type PWD and it will show you what it is here. Then you can toggle on and off the warnings. I will keep it on here sometimes. If you, for example, have a hard time doing the integration and then the software, the ODE solver is trying to figure out the right time step, there might be a little bit of warnings coming on, for example, nearly singular matrices until it stabilizes. So you may want to turn it off for making the simulations faster. But here, since we have only one simulation, I will keep it on and we'll do the demonstration with all the warnings on. Once I do that, I can run the simulation using this PBE simulation engine, which integrates the ODE set, as I mentioned before. I put a tick and talk here to see what I would get in terms of integration time. I will go over this a bit later once I run the demo as a whole. Or maybe we can run it right now and then come back and take a look at the rest of the script in a bit. Okay, it takes some time. I will go down a little bit. It takes around 1-2 minutes for the simulation. So here I have calculated some auxiliary outputs. So what is the volume of the reaction as a function of time? Or how much solid is forming as a function of time? Then comparison with what you would have if everything reaches equilibrium at every time step. These are important to calculate because not only sometimes you need them, for example, to calculate the yield of precipitation, but also these are important from the point of view of cross-checking if your calculations are correct. And I will go over this in a little bit once the run has finished and the figures show up. Then you have also the possibility to calculate a variety of outputs, so crystallite sizes or particle sizes, surface areas as a function of time, in this case crystallite surface area and particle surface area. And you can also cross-check what is the situation in terms of supersaturation ratio with respect to different phases. And then I have here put all of these information. I calculated not all of them, but most of them here more or less. So in the form of some plots to show you also some of the outputs. Okay, so now the run is finished. As you see, this maximize function automatically maximized all of the windows. I have 3 figures, but before going over those figures, I would like to go back here and show you, for example, on this laptop, which is not a very powerful one, I would say. It has only 2 cores and the CPU is not a top-notch CPU. The run took like 82 seconds. Of course, on a better workstation, instead of a laptop, you would get something smaller. It highly depends on the machine, but more or less, it changes between something around 10 seconds to 2 minutes, depending on the machine. Then this is the runtime for a large number of speciation calculations we had here. And what is that? So let's take a quick look. Here we have the kinetic speciation. So if we go back to our paper in the Journal of Materials Chemistry A, we have this so-called kinetic speciation, which is basically different speciation parameters like pH, ionic strength, and the amount of different aqueous species as a function of time. In the previous version, of course, it was embedded, but here we are only receiving a number of outputs from population balance engine, which can then later be used to calculate, or let's say back calculate, any other output. So what we are getting as the output is the number concentration of particles as a function of time, quadrature points, moments. So basically, these quadrature points are weights and abscissas. We have the moments of those of the distribution, particle size distribution as a function of time. In this case, with 3 quadrature nodes, we have 6 moments, and the elemental concentrations as a function of time. Then you can use these inputs and calculate different things. As I said, for example, surface areas or crystallite and particle sizes. Any kind of output you need to calculate can be estimated based on only those outputs. And the reason I did this is because if we try to save all these results at every time step, then you will have a huge amount of data, and it takes up a lot of space and makes everything slower. This is very important when you are doing, for example, optimization, or for example, when you are doing uncertainty sensitivity analysis, because these data are easily accessible. So here, for example, in less than 3 seconds, 2.2 seconds, the kinetic speciation was obtained. Let's see for how many? For 289 data points that we have. It's amazing. It doesn't take any time, so you don't have to worry about it. Now let's take a look at the some of these plots, see what we get. So here I have the 0th moment. So basically we have a number of crystallites as a function of time per unit volume of the reaction medium. So here in this particular case, we have a huge number of crystallites because we have both primary nucleation, secondary nucleation, pretty low values for interfacial tension. And as you see, for example, close to the end, you can see, for example, we have 2.2 to the power of 2.2 times 10 to the power 22 crystallites per cubic meter of solution. Everything here is everything in the calculations, more or less, is in SI units unless otherwise mentioned. This second plot shows you the crystallite thickness and particle edge lengths as a function of time. So I will not describe these outputs in any detail, because you can go back to our materials chemistry A paper and read the interpretations. Then we have quadrature nodes and weights. Here we have the weights, and here we have the nodes, of course in nanometers. Then we have calcium, elemental calcium and elemental silicon as a function of time. So these are the values that you would get kinetically. And the dashed lines are basically the values predicted if equilibrium is reached at every time step. So if I zoom in here, maybe you can see better. We can cross-check if everything is working fine. So these circles have to be always above the dashed line, because when we are consuming elements like calcium and silicon to precipitate solid, if everything goes to equilibrium, the values in the aqueous solution should drop more. But kinetics doesn't allow for this to happen, and we have less drop. Eventually, though, you approach these values. If I zoom in here after, let's say, 12 hours, you see that your calcium is approaching this equilibrium value, and also your silicon is. On the other hand, for the two other elements in aqueous solution, we have nitrogen aside, gaseous nitrogen aside, the elements are not participating in any solid formation. Therefore, there is no difference between the prediction of kinetics and prediction of thermodynamic equilibrium, because, as I said, it is not participating in any solid formation. Everything is dictated by equilibrium. We'll close this one. Let's go to the second figure here. Another cross-check is the amount of solid that is forming predicted by solid-liquid equilibrium has to be always higher than the kinetic prediction, and this is again the case. It's always below, and as we go close to the end of the process, we reach more or less the equilibrium value, which when these two are exactly the same, we have 100% yield. Then here I have pH as a function of time. So in this particular system, pH is around like 12.5 3, 4 at the end. At the beginning, it's something around 7. As soon as I start the injection, of course, I'm injecting sodium silicate and sodium hydroxide, it goes up. The ionic strength goes up and down. So at the beginning, where I don't have much precipitation, it goes up. Then we have precipitation, we have a drop of ionic strength, but then we have again another build-up. And once I stop the addition, it again drops. So the value is something around, let's say, 60 millimoles per kilogram water. Then I have the kinetic speciation for calcium-containing species here. Here, the most important calcium species are these 3. The last one, let's say, is calcium HSiO3 plus is literally 0 always. And as for the silicate species, or silicon species, better say, the most abundant one is this calcium silicate ion pair, followed by let's say this yellow one is this HSiO3, and so on and so forth. And the third figure here is, let's say, some representative results from, for example, supersaturation ratio. So this black one is the supersaturation ratio with respect to CSH. It goes up, at some point drops due to nucleation, and goes down further due to growth, and reaches almost equilibrium, close to 1, as you see here. Portlandite, on the other hand, is always undersaturated in this system. You can, for example, add a crazy amount of sodium hydroxide, increase the temperature, and then you may also have Portlandite precipitating, but the kinetic code, as I mentioned, cannot deal with simultaneous precipitation. It only can give you the supersaturation ratio of more than 1 solids. Then here I have also plotted the critical size of nuclei, primary nuclei and secondary nuclei. Of course, secondary nuclei are slightly smaller, hence their formation is easier. This is compatible with lower activation free energy against their formation. So, okay, that's pretty much it. Please don't hesitate to play around with the parameters, add some species, play with kinetic parameters, play with the temperature, and see what you get. And thank you very much. I hope you enjoy using our code, and please send me an email if you have any questions.